Okay, so in this puzzle we will be looking at volumes of solids with known cross sections. We will be looking at the disk method, and we will be looking at the washer method. Okay, so a lot in this puzzle going on. Let's first start off with cross sections. If you were to go to your web page, your class web page, and under the Student Resources tab, and when you clicked on this Student Resources tab here on the side, you'd get this link down here near the YouTube icon that says Wolfram Demos. Okay, so when you click on Wolfram Demos, this comes up. And in this search bar right here, what I would want you to input would be the following: cross-section volumes. Now, with cross-section volumes, we're going to look at different cross-sectional volumes that they have programs for on this website. Now, I'm clicking on this particular one because there's many different ones I want to show you as an introductory. And I'm going to click on this download demonstration as CDF right here. And if you can, it's free, but if you want to upload this software and whatnot to your home computer, you're more than welcome to. So I clicked on that, and then I'm going to click on this and open it and show you what the program looks like, because you're able to interact with it. Okay, so you can actually manipulate certain things of the program, such as the length of its base, the cross sections of their squares, circles, and whatnot. Just so that you can better visualize this, because this does get a little intimidating if you can't visualize it on a 3D scale. Okay, so three-dimensionally we're trying to visualize these so that when we do the integrals, they're not that bad. Okay, so let me go ahead and open this one and show you first off what we're talking about as far as three-dimensional shapes. So what you see here is, if you notice, the cross sections of these are what look as rectangles, and then this looks like it's going to be a semicircle. You have other ones way over here that are semicircles. So it almost looks like, if I were to compare it to something three-dimensionally that we already know, it almost looks like a cylinder, to where the base is a cross-section circle. So all it is pi r squared times height, because of the fact that you are stacking them with a bunch of different units that, like if the height was 10, it'd be pi r squared times 10. Okay? That's giving you a volume. So the fact that I multiplied the area, cross-section area of pi r squared, times a given height, it gave me volume. Okay, so what we're going to do here is we're going to integrate some stuff. For instance, like, let's say that I have this shape here that you see right here with these cross sections. It looks like, almost like an amphitheater of some sort. Okay, so if I looked at this and I wanted to find the volume, these cross sections are not going to be squares like my cylinder example. These would be semicircles, which are pi r squared divided by 2. Now, to multiply by the height of this thing, instead of multiplying by h, what we're going to do is we're going to integrate it on an actual interval. Okay, and this h is what we're accounting for right now. So this one has, let's say this was positive 4. So it's going to be, here's the, if you haven't seen, or if you haven't noticed by now, this is the y-axis, this is the x-axis. So here's x, here's positive y. So it's almost like you're looking down perspective-wise. You're looking down, so your eyes over here, whatnot. I know it's a bad drawing, but you're looking down as far as the x and y axis, and you're integrating from 0 to 4. Again, low to high when you're looking at it in terms of y. So this area formula that you have, now there's some things that we have to change here, but this is basically the gist of it. I'm going to integrate this area, and it becomes dy or dx. We're going to talk about that here in a bit, but I'm integrating from 0 to 4. So if I integrate the area, this 0 to 4 is the interval that otherwise would be known as h up here with my cylinder example. Okay, so let's see what this looks like as far as on the program that we have. Now I can manipulate this. Okay, so moving this around, you could do this at home. It kind of helps you understand what these pictures look like. Okay, so like right here, you see the base region is a circle. So if I looked at the base region, it is a circle. Okay, if I wanted to change it to a square, I could click on that. I could make it a triangle for the base. I could mix it up. Different things that I can do, and I'm going to go back to the circle. So the base is a circle. Okay, and you see this model right here as far as showing you what the base region looks like. Okay, so I have squares that are cross-section perpendiculars, perpendicular cross-sections right now. Instead of squares, I could make them equilateral triangles. And you see the equilateral triangles. The base is still a circle, but the cross-sections are these equilateral triangles that you can see. Let me go ahead and highlight them real quick for you. Like this is a equilateral triangle. This big one would be a huge equilateral triangle. And notice that it's going throughout the shape. So it's like going through the shape three-dimensionally. Okay? So let me go over here and alter this a little bit more, do semicircles. And again, the base is still a circle, but the cross sections are semicircles. And then you can have rectangles. So rectangles, semicircles, equilateral triangles, and squares. That's what we're talking about as far as cross sections. Okay? So when I integrate a cross section, the way I'm trying to give an example of my original half semicircle here, when I integrate area, it yields volume. Just like we've been doing with area between two curves. We're integrating a function, we get area. Okay? And with this in mind, we know, like when we did derivatives, if I took the derivative of the volume function for a, let's say, a sphere, 4/3 pi r cubed. This is the volume. If I derived it, I would get, with power rule and whatnot, 3 times 4/3 pi r squared. Now those cancel out and I get 4 pi r squared. And by now you should know this is the surface area of a cylinder, or sorry, of a sphere. So when I derive volume, I will get area, but when I integrate area, I get volume. Okay, so this right here is the big key as far as what I'm trying to show you right now. Okay, so let's go back, or let's keep going to our examples that we have, okay? So the examples that you see here, the cross sections that are perpendicular to the x-axis. So if I were to go back to my shape as far as perpendicular to the x-axis, it would look something like, and I'm going to draw this as best as I can, because it is a little bit of three-dimensional rendering. My x-axis looks something like, let me show you, perpendicular to the x-axis. So here's the y-axis, and here would be the x-axis. Okay, so all these slices that you see, let me go ahead and highlight one in yellow. This is a square, and it's perpendicular to the x-axis. Now, let's say that I saw a slice that went way over here, then went up, and then came over here and came down. This is a big square as well. Okay, so let me draw this a little bit better. Okay, and this is going to be perpendicular to the x-axis, because if I looked at it from the area point of view, that first square that I drew would be right, let me draw it in red, would be right here. That second one that I drew would be closer to here. But again, they're popping out of the picture because of what you see as far as the cross sections. Okay, so now let's go back, and we will say perpendicular to the x-axis, they're going to be vertical slices. Okay, vertical slices, because you could draw yourself a little XY graph, and here's X. If it's perpendicular, it's going to create a 90-degree angle. You could see that this is going to be dx. Okay, so dx, and then perpendicular to the y-axis, those will be horizontal, because here's the y-axis. Let me highlight it real quick. Highlighting the y-axis, anything perpendicular to that will be a horizontal line, because that creates a 90-degree angle. Okay, so these will be dy's, and horizontal slices. So these are important as far as how we set in terms and in respect to for our integrals. A of x says the area formula is in terms of x. So I'm going to integrate it in respect to x, there's that respect to, and all I need to do is from low to high, or from A to B. Okay, the other one, because it's in terms of y, it's going to be a of y dy. And a of y is representing the in terms of, so in terms of y, and the dy piece is representing the in respect to. So, and then still from a to b. Now, just a little recap, a to b are low to highs. So when I say a, you should be thinking low x if it's a of x, low y if it's a of y. Then b is a high y if it's a of y, and the b here is high x if it's in terms of x. Now, let's go ahead and do our first example. Set up the integrals needed to find the volume of the solid whose base, okay, so whose base, and if I go back to these pictures, the base is a circle, okay? You saw the base being a circle, and here's that cross-sectional shaded base region, and I could have made it a square, and you see it changed to a square, and the base is now a square. The base is blue if you haven't figured that out by now. So the base, going back to a circle, it's just different shapes, okay? So we will go back here, and the base is going to be whatever is created by these two functions or lines that are bounded. Okay, so let's go ahead and color coordinate some of this. I will color coordinate y is equal to x squared to be red. And we will color coordinate the other one to be blue. So negative 2 plus 3, negative 2x plus 3 looks something like that. And with this in mind, we're going to look at perpendicular to the x-axis. So I should be thinking dx or vertical slices. So I should be doing this. This is why I asked you to do this so very neatly and whatnot on last day's units or the yesterday's notes. Okay. So looking at this, if you were to do a 3D rendering, this is y, this is x. You could look at it like this. So I'm laying it down and kind of giving it a three-dimensional view to it, to where its z-axis will be coming out of the picture, if you will. Okay, so it's like, let's say that you were standing, no, I think you could see it from here as far as the rendering goes. Let me draw the function x squared. So x squared is up here. It's like laying down, if you will, and that negative 2x plus 3 is here, so that each perpendicular, I'm going to do it in black, is going to be perpendicular to the x-axis. And you see them, they're vertical slices, and it's basically what we were showing here. We showed the three-dimensional rendering here with the comparable base that's being a circle here. So I'm doing the same thing in my notes. This is the base that is saying, it's describing that piece over here, right? This base is the same as this base, okay? And then the 3D rendering is going to be over here. So they're going to pop out of the picture. Now it's a little weird as far as trying to do these pictures by hand. Like for instance, if I said that they were going to be rectangles, I'd come over here, and with this base, I'd create a rectangle that would be popping out of the page, if you will. Okay? And then like over here, if I had another base and I went up, this would be a rectangle. So it's all these rectangles put together that are now popping up out of the picture and giving it that three-dimensional rendering that you see here. You know, it's just like I was showing before. Let me try to see if I can do this a little bit clearer so that you can see those axes as far as what they look like. So here's that y, here's that x, and then you can see of how it's popping out of the picture. And if I were to highlight one of the cross sections, let me do that in red. I could show like this one right here comes over here, comes down, and then it has like this base coming through. And then you should see by now what it looks like as far as three-dimensionally, like standing up from the picture, if you will. Okay? So what we're going to do is, we know to find the volume, we need to integrate some kind of area. And I'm going to do a of x because of the fact that we have vertical slices. So it's a of x dx. So I need to find an area formula that is written in terms of x. So rectangles, we know the area formula for that is base times height. So base times height is going to be what I'm going to put here for my a of x. Okay, so looking at this, I need to figure out what represents the base and what represents the height. Well, I'm saying a height of 4. Okay, it will pop out of the page with a height of 4. So if it pops out, this has a height of 4, and this has a height of 4. All these will have a height of 4. It's just that they get real skinny there at the end, and they get wider as far as in the middle of it, where the base has more room to have more width, if you will. Okay, so here's one right here with the small one. Then the second one has just a little bit wider, but the same height of 4, and then so on and so forth. So it gets smaller on the ends and bigger in the middle because of the fact that the middle has more. It depends on each of these bases as far as how big is it. Okay, so with that being said, the height is going to be 4, so area is equal to base times 4. Okay, and then the base. The base is going to change. At the very end, the base will be small. In the middle, the base will be big. And back at the end, the base will be small again. So because the base is changing, we have to leave it in variable form. So this length right now, what would be written as? Okay, so like this is B, and this is B. So how do I find B? Because it's changing, it's going to be that length as far as the top minus the bottom. Okay, so I'm going to say the top function is negative 2x plus 3. And if I subtract the bottom function of x squared, technically this is b. And it'll change throughout the x's because, like I said, at the ends it'll be smaller, and in the middles they'll be bigger because of the fact that it's more length between the two functions. Okay, so that's b, and it's changing. It's ever changing throughout this entire interval. Okay, so what I'm going to do is I'm going to integrate now from low to high. Because these are perpendicular vertical slices, I need to find what this x value is right here. Then I need to find what this x value is right here, because it will be from A to B. Okay, so real quick, I'm going to set them equal to each other. X squared is equal to negative 2x plus 3. And you can use a calculator, or you can do this by hand. Some of them you'll need the calculator. Plus 2x minus 3 is equal to 0. And I get x plus 3, x minus 1, because they factor out, and you get 1, and you get negative 3. So at negative 3, that's A, and at 1, that's B. So I'm going to have a negative 3 to 1, and now I need to put this equation here, my A of x. My A of x will come over here. I'm going to go ahead and write it. It will be negative 2x, and now, again, this is my x, my b term. So negative 2x plus 3 minus x squared. All of this is b. And I'm going to multiply this all with 4, because they all have the same height of 4. Now I'm not going to put that 4 there. I'm going to choose right now to just go ahead and put it way out here. And the reason why I can do that is by constant multiple rule. I can bring that 4 out and then just put dx there. So it's going to be the integral from negative 3 to 1 of 4 times this. And again, it's base times height. My height was 4, and my base was this entire integrand. And because the base is changing throughout, we're going to put it as a variable form of negative 2x plus 3 minus x squared. Notice my use of parentheses. This will give me the volume as far as the answer. So let me go ahead and do that into the calculator. So over here I will click on the definite integral. We are going to go from negative 3 to 1. And the function going back was negative 2x plus 3. So I'm going to go ahead and put that in parentheses. Negative 2x plus 3, close, minus, and it's going to be the x squared. And I'm just going to get in habit as far as putting the parentheses on especially this next one right here, this x squared piece, because this negative will sometimes distribute. Okay, this negative right here will distribute throughout that function there, if and only if you have like this function here, if and only if you have plus and minus some stuff. Okay, so just make sure that you have that negative. Just make sure that you have the parentheses there, because the negative. Again, let me highlight the parentheses. These parentheses are what I'm talking about, because this negative can distribute if it's a polynomial, if it's something more than just one monomial. Okay, so let's go back, and we're going to finish it up with putting dx and then of course at the very end we'll multiply it by 4. So I'm going to just go ahead and put enter, multiply by 4. I could have done that at the beginning up here on the first part by putting 4 in the very front, okay? And you'll get an answer of 42.666 or 42.667. Again, rounding to 3 decimal places. So is equal to 42.667, and it's units squared because it is a bounded area. Bounded areas right here are always positive. We talked about that in class already with areas between two curves. So 42.667 units squared. And now we're going to move on to the semicircles. Okay. So what you first need to ask yourself is, what is the equation to get the volume? Okay, so the equation to get the volume will be the integral of the area. Okay? So if the integral of the area, I need to come up with an area formula. It's pi r squared divided by 2. Okay? These semicircles are the cross sections. There's a half a circle, if you will, like the rest would go down here, but you're doing half a circle, so it's pi r squared, and you're going to integrate it. So let me highlight it in green. These bases of these semicircles, so here's a base of this semicircle, will correspond to up here. Okay? So as far as where it's going to be on the graph. So just like I highlighted in green up here, that's where it's going to correlate to the cross sections. And again, we can look at that from this picture of there. If you wanted to change it to semicircles, you can see that this base that I'm speaking of, let me go ahead and highlight it, this base right here of this particular semicircle is going to correspond with the base over here as far as the picture. Okay? So now, if I were to go to this three-dimensional rendering, they're no longer going to be rectangles. So real quick, just for practice, x, y, so here's x, here's y, z comes out, okay? And I still have those pictures. Let me do both of the functions in blue now. So there's that x squared, here's that other one. It's still perpendicular to the x-axis, so there's still going to be vertical slices if you were looking from down from an aerial point of view. So let me go ahead and do those in purple. So here are the slices that are perpendicular to the x-axis. And coming up from there, I'll go ahead and do it again in green, are these semicircles. So here's a base, there's a semicircle. So I'll shade that in. Smaller on the end, smaller semicircle. Bigger, closer to the center, bigger semicircle. And you're just going to piece them all together where they look something like that. You can see the semicircles are bigger in the middle, and they're smaller on the ends, still being the base a circle. Okay? So now we need to figure out what is our a of x. Okay, so our a of x, let me go ahead and write that in. Our a of x is going to be in respect to x, and in terms of x, and in respect to x, again, because it's vertical slices, otherwise perpendicular to the x-axis. Now, we already know what our intersections were. Our intersections were from -3 to 1, and that's where we set them equal to each other from the last, for part A, and we saw for their intersections. We just need to make sure that this goes over here. So pi r squared divided by 2. I should see pi over 2 right now and know that I can bring that out. Pi over 2 is a constant, okay? But the r squared, the leftover, whoops, didn't mean to erase that. The leftover variable, that's what's going to go over here as far as the variables in terms of x, okay? So we need to find a way to write that r squared from these two functions. Because technically, the length of r squared, okay, or sorry, the length of r, that is, the length of r will be half of whatever that is, okay? So if I'm looking at this entire semicircle right here, what I highlighted in green, that's a diameter. If I divide that by 2, let me go to the picture. Here's a radius. Here's a radius. And here's a radius. It's half of the base, okay? So what I'm going to do is I'm going to say the top minus the bottom divided by 2 is r. Okay, so the top function we've already identified is x squared. Okay, so x squared minus the bottom function, which is negative 2x plus 3. And again, remember those parentheses. That's where people mess up. So the top minus the bottom gives me the diameter, but I want to divide that all by 2 because that yields the radii that I'm highlighting over here that were in red. Those are the changing length of the radii as you go throughout that entire interval from negative 3 to 1. Okay? The only thing that I have to do now is square all of this because it is pi r squared divided by 2. Okay? So all that's in the brackets right now, that represents r. And then dx because it's going to be vertical slices. Okay, so semicircles. If I were to go ahead and put this in the calculator, it's going to be, well, let me go ahead and put this pi over 2 right now. So pi over 2, it's going to be times the integral from negative 3 to 1. And then it's going to be this top minus the bottom, so on and so forth business. And I'm realizing right now before I get the emails that I switched my top and bottom on accident. I should not have it like that. Those need to be flipped, okay? Because I knew I was going to get some emails. So the top function is negative 2x plus 3 minus the bottom function, which is x squared. So let me go ahead and put that in the calculator right now. So control divide, parentheses negative 2x plus 3 minus x squared. And then we're going to put this all over 2. So negative 2x plus 3 minus x squared all over 2. And then we're going to put that in respect to x. So let me put an x right there. Okay, so negative 2x was the top. Negative 2x plus 3, that is, was the top. Technically, this is the top, and this is the bottom. That's why I had to switch it up in the calculator. And then put it all over 2, raise it to the second power because you're squaring that r, and then go ahead and press Control Enter to see what your value would be. Okay, so let me go ahead and put all this, before I forget, all this is r. So all that top minus bottom yields the diameter. I will divide that by 2. Now I have r, and then I will square it. So all these little pieces, that's what makes this unit difficult, or the unit that involves volume. It's because you're trying to figure out what little pieces of equations that involve pi r squared divided by 2, or base times height, that you're going to represent as your integrand. Okay, so in summary, the hard part of this example was trying to figure out that this minus this gave me the diameter, so that when I divide it by 2, I have r right here. Okay, and r, going back to my equation, the easy equation that I was starting off with, would be right here. So r squared, constant multiple rule, control divide, or control enter that is, and my answer is 13.404. So 13.404 units cubed, and I made a mistake there. So units cubed before I get that email. This is volume, therefore it would be 13.404 units